The day is ordinary until the sky blinks one white flash, as if the horizon took your picture. No sirens, no contrails. 10 seconds later, a wall of pressure hits like an invisible fist. Windows burst. Car alarms scream. The news won't call it a bomb. Something smaller and far stranger just hit Earth at 99.99% the speed of light. That is the nightmare we're unpacking. Because near light speed, physics stops behaving politely. Time stretches, matter flattens, air turns to armor. Tiny objects carry ridiculous amounts of energy. This isn't science fiction. It's the extreme end of things the universe already does to single particles every day. Start with one number. At 99.99% of light speed, the relativistic factor gamma is about 70.7. In plain English, the kinetic energy becomes roughly 69.7 times the object's rest mass energy, mc squared. A 1 gram object paperclip weight now carries about 3 times 10 to the power of 15 joules. That's tilde 1.5 megatons of TNT. 10 grams, approximately 15 megatons. 1 kilogram, 1,500 megatons, 1.5 gigatons. Even a milligram, a literal grain of sand, packs tilde 1.5 kilotons. Energy climbs brutally as you add nines to the speed. Now picture that sand grain entering the atmosphere. You won't see a long, lazy fireball. From the grain's point of view, Lorentz contraction squeezes the oncoming air into a thin, ultra-dense slab. To us, the grain smashes that slab and vaporizes almost instantly. The first atomic layers absorb stupendous energy in billionths of a meter, ripping electrons free and turning matter into a roaring plasma. The event looks less like a meteor streak and more like an instantaneous airburst. A flash across the spectrum, a shower of high-energy particles, and a crushing shockwave. Nature shows us a tiny version. Ultra-high-energy cosmic rays, protons, and nuclei from supernovae and black hole jets strike our air with energies of tens of joules carried by a single particle. They trigger extensive air showers, avalanches of secondaries that splash across square kilometers. Earth's magnetic field is a good bouncer for lower energy riffraff, but the most energetic bullets barely notice it. Thankfully, cosmic rays are microscopic. Our pebble is not. What happens next depends on size. A milligram sand grain dumps its energy high in the stratosphere and mesosphere, a flash brighter than the sun for a heartbeat, a broadband radio crack, and a pressure wave that circles the globe. A marble 10 grams plunges deeper before it vaporizes, delivering on the order of tens of megatons in an airburst that would flatten forests, strip roofs, and ignite fires across a wide region beneath the detonation. A 1 kilogram projectile would be catastrophic anywhere it detonates over land or sea. Above an ocean, the blast would loft seawater into the sky, drive a wall of vapor and spindrift outward, and send tsunami-like disturbances rippling toward distant coasts. Over a city, it would mean shattered infrastructure, secondary fires, and a maelstrom of flying debris. Could our magnetic shield save us? Not from neutral matter. Magnetic fields steer charges. Rocks don't care. Even if the object were charged, at these energies its path would hardly bend before it hit air. The real hero is the atmosphere itself, roughly 10 meters of water, equivalent above every square meter of ground. It turns kinetic energy into light, heat, and shock before debris can gouge into bedrock. That's why most natural meteors burn up, but most assumes ordinary cosmic speeds tens of kilometers per second, not 0.9999 c. How much warning would we get? Almost none. Our surveys, Pan-STARRS, Atlas, and soon the Rubin Observatory's LSST are built to find objects crawling, cosmically speaking, at tens of kilometers per second. A relativistic intruder makes a mockery of our timelines. From the moon's distance, about 384,000 kilometers, an object at 99.99% C arrives in roughly 1.3 seconds. From Mars at a good alignment, a few minutes. From Neptune's orbit, hours. There would be little sunlight to reflect, little infrared to pick up, and almost no time to react. If this is so bad, why hasn't it happened? Because nature struggles to fling macroscopic chunks to ultra-relativistic speeds. Accelerating a gram to 99.99% C demands energy on the scale of strategic weapons. There are no known astrophysical railguns for rocks. Charged particles ride magnetic fields, but neutral clumps don't couple well. Even in the fiercest accelerators, the shock fronts of supernovae and the collimated jets of active galaxies, what gets boosted are individual particles, not pebbles. Thinking through the nightmare still teaches us where our protections end. Magnetic fields help with charged rain from space, but neutrality beats magnets. The atmosphere is our last shield, but at extreme speeds it delivers the blow as an airburst. And our planetary defense playbook detect, track, nudge assumes weeks to years of warning. Relativistic threats erase the calendar. If prevention fails, only resilience remains. Infrastructure that tolerates shock and heat. Power grids that ride out EMP-like surges. And emergency systems that function when radio goes silent for a moment. Here's our roadmap. First, the clean math of ultra-relativistic energy and momentum, and how the numbers balloon as you add nines to the speed. Then, how the atmosphere couples to an intruder, fragmentation, where energy is deposited, and what spectra of light and radiation would be seen from orbit and ground. We'll scale from sand grain to marble to car to house-sized asteroid. Along the way, we'll ground the story in real measurements, from cosmic ray observatories and meteor surveys to NASA and ESA studies, so every jaw drop has math behind it. Before we dive in, keep one truth in mind. At 99.99% of light speed, even the smallest things can carry civilization-scale consequences. A grain of sand becomes a weapon. A paperclip becomes a city killer. A car becomes a global event. The physics isn't malicious. It's simply relentless about the price of almost light speed. Ready? Let's open the numbers and see what a relativistic airburst really does over land and sea. Let's put firm numbers under the drama, because the numbers are the drama. At 99.99% of light speed, the relativistic factor gamma is about 70.7. Kinetic energy is roughly gamma minus 1 times mc squared. Momentum is gamma times m times v. Two short rules that turn terror into arithmetic. Take a gram. Its rest mass energy, mc squared, is about 9 times 10 to the 13th joules. Multiply by gamma minus 1, roughly 69.7, and you get around 6 times 10 to the 15th joules. That is about 1.5 megatons of TNT. A single paperclip's mass with a strategic weapon yield. Scale to a kilogram and you are at 1.5 gigatons. The exact decimal is unimportant. The scaling is the message. Add nines to the speed and the bill explodes. Now translate that energy into what the atmosphere actually feels. A near light speed object does not carve a long meteor trail. It effectively detonates inside the air it meets. Lorentz contraction squeezes the oncoming air into a thinner slab. The first atomic layers of the projectile and the air strip electrons and turn to plasma. Most of the kinetic energy is deposited within a very short column. The result looks like an airburst, an instant flash, a hard shock, and a hot, expanding cloud. Where the dump happens sets the damage. A milligram unloads high in the mesosphere. You get a blinding blink across ultraviolet and visible bands, a crack of radio noise, and an infrasound pulse that laps the globe. A 10-gram marble penetrates deeper into the stratosphere or upper troposphere before it fully vaporizes. That puts the pressure wave within reach of cities. Windows implode, facades crack, and people miles from the center feel the delayed boom. We have a yardstick for airbursts. In 2013, a 20-meter stony meteor exploded above Chelyabinsk with a yield in the hundreds of kilotons. The shock shattered glass across the city and injured over 1,000 people, mostly from shards. That was at ordinary cosmic speed. tens of kilometers per second. At ultra-relativistic speed, the light is harsher, the column is shorter, and the coupling to air is more violent. You trade a long, glowing streak for a denser, punchier burst. The sky would speak in particles as well as light and sound. High-energy collisions trigger extensive air showers, avalanches of electrons, positrons, muons, and photons spreading sideways and downward. Ground arrays would register a sudden spike. All sky radio instruments would hear broadband hiss from the expanding plasma and the racing charges. Satellites would see a brief X-ray and gamma flash from below, a local flare rather than a celestial burst. Could Earth's magnetic field help? It helps with charged particles. A magnetic field curves their paths. Neutral matter is indifferent. Even a charged projectile at these energies carries such momentum that its path would barely bend across the magnetosphere's thickness. The magnetosphere is a superb shield against the sun's wind and most cosmic rays. Against a neutral pebble screaming at 99.99% C, the shield that matters is our air. Air is thicker than it looks. Above each square meter of ground sits roughly 10 metric tons of atmosphere, about 10 meters of water equivalent. That mass is our last armor. As the projectile shreds into a spray of atoms and ions, the armor soaks up the energy and re-radiates it as light and heat. That is good, because it stops deep cratering. It is bad because it compresses the energy into a shock and a brief furnace in the sky. The day is ordinary until the sky blinks one white flash, as if the horizon took your picture. No sirens, no contrails. 10 seconds later, a wall of pressure hits like an invisible fist. Windows burst. Car alarms scream. The news won't call it a bomb. Something smaller and far stranger just hit Earth at 99.99% the speed of light. That is the nightmare we're unpacking. Because near light speed, physics stops behaving politely. Time stretches, matter flattens, air turns to armor. Tiny objects carry ridiculous amounts of energy. This isn't science fiction. It's the extreme end of things the universe already does to single particles every day. Start with one number. At 99.99% of light speed, the relativistic factor gamma is about 70.7. In plain English, the kinetic energy becomes roughly 69.7 times the object's rest mass energy, mc squared. A 1 gram object paperclip weight now carries about 3 times 10 to the power of 15 joules. That's tilde 1.5 megatons of TNT. 10 grams, approximately 15 megatons. 1 kilogram, 1,500 megatons, 1.5 gigatons. Even a milligram, a literal grain of sand, packs tilde 1.5 kilotons. Energy climbs brutally as you add nines to the speed. Now picture that sand grain entering the atmosphere. You won't see a long, lazy fireball. From the grain's point of view, Lorentz contraction squeezes the oncoming air into a thin, ultra-dense slab. To us, the grain smashes that slab and vaporizes almost instantly. The first atomic layers absorb stupendous energy in billionths of a meter, ripping electrons free and turning matter into a roaring plasma. The event looks less like a meteor streak and more like an instantaneous airburst. A flash across the spectrum, a shower of high-energy particles, and a crushing shockwave. Nature shows us a tiny version. Ultra-high-energy cosmic rays, protons, and nuclei from supernovae and black hole jets strike our air with energies of tens of joules carried by a single particle. They trigger extensive air showers, avalanches of secondaries that splash across square kilometers. Earth's magnetic field is a good bouncer for lower-energy riffraff, but the most energetic bullets barely notice it. Thankfully, cosmic rays are microscopic. Our pebble is not. What happens next depends on size. A milligram sand grain dumps its energy high in the stratosphere and mesosphere, a flash brighter than the sun for a heartbeat, a broadband radio crack, and a pressure wave that circles the globe. A marble 10 grams plunges deeper before it vaporizes. delivering on the order of tens of megatons in an airburst that would flatten forests, strip roofs, and ignite fires across a wide region beneath the detonation. A 1-kilogram projectile would be catastrophic anywhere it detonates over land or sea. Above an ocean, the blast would loft seawater into the sky, drive a wall of vapor and spindrift outward, and send tsunami-like disturbances rippling toward distant coasts. Over a city, it would mean shattered infrastructure, secondary fires, and a maelstrom of flying debris. 1 gram is the paperclip that keeps showing up in your nightmares, 1.5 megatons. Dump that in the lower stratosphere or upper troposphere, and you get a continental-class sonic event. The overpressure field leans forward along the trek because the fireball carries momentum while it grows. Downrange towns get a stronger shove than cross-range ones at the same distance. Thermal radiation can ignite dry vegetation and plastic rooftops within tens of kilometers given dry, windy conditions. 10 grams, think a marble rises to 15 megatons. Castle Bravo territory but released aloft. This is not a nuclear device, so you don't get the prompt fission gamma spike and classic EMP. You still get ionospheric turbulence from flash-heated air and the charge avalanche, bending radio and GPS for minutes. At tens of megatons, the one-psi, window-breaking, contour reaches far beyond a metropolitan area. Even hardened facilities may be stressed by a fast, azimuth-dependent shock. 100 grams is 150 megatons. Now the footprint spans a small country. Over the ocean, the main coupling is still atmosphere, not water. The blast happens above the surface. But a fast pressure step marching over the sea can seed meteotsunami-like waves and coastal seiches. Expect centimeters to decimeters on far coasts, and worse near enclosed bays and shelves. Nearby ships would be hammered by the pressure wall, spray, and spindrift lofted by the downward push. A kilogram is 1.5 gigatons. That's small asteroid energy without a crater, because the atmosphere does the stopping. The shock would wrap a continent. Infrasound would circle the planet for days. Stratospheric chemistry would notice. Nitrogen oxides spike. Ozone dips regionally. And for weeks high, latitude auroral activity could ride the disturbed ionosphere. Beneath the burst, the thermal pulse could char agricultural belts and forests over a multi-state or multi-country region. Where does the dump happen? Think atmospheric column. Above your head sits about 1,030 grams per square centimeter, roughly 10 metric tons per square meter, equivalent to 10 meters of water. A relativistic object disassembles as soon as it is battered through enough column to shred itself. Milligrams lose the fight high up. Grams survive longer. By tens to hundreds of grams, the hottest phase occurs around the tropopause to lower stratosphere. What would sensors record? Weather satellites would catch a saturated visible and infrared flash, then a rapidly expanding cloud top with odd spectral colors from ionized nitrogen and oxygen. Space-based lightning instruments would trigger because they watch for fast optical transients. GNSS networks would see a brief regional position error as the ionosphere ripples. Ground arrays would log an extensive air shower, electrons, positrons, muons, and photons racing outward in a thin pancake. On the ground, the hazard hierarchy is consistent across sizes: flash, shock, debris, then fire. The safest reflex is universal. Look away from the flash, shelter from glass, wait for the boom, help those cut by shards. For coastal communities, add one more. If a sudden pressure step passes, barometers jump, and a minute later the sea behaves oddly, move upslope. A meteotsunami can arrive quietly and then surge. What about armor or field shields? The best armor we have is already in place: air. It is a Whipple shield on a planetary scale. The same principle spacecraft use. Let the first layer fragment the projectile, so the second layer absorbs a mist, not a bullet. Magnetic fields don't help against neutral matter. Even a charged macroscopic projectile would barely bend at these energies across the magnetosphere. A local plasma bubble shield around a city would be a candle in a hurricane. Where do these numbers come from? From first principles relativity, E-bang 69.7 m/s² at this speed, meteor physics column models, and blast wave scaling laws for explosions in air. Chelyabinsk provides a modern calibration. Historic nuclear test data anchor how overpressure and thermal flux scale with yield and burst altitude. Cosmic ray observatories show what an extreme air shower looks like. NASA and ESA datasets, USGS summaries, and the CTBTO infrasound network supply the empirical backbone. So the size ladder is clear. Milligram equals local sky, flash. Gram, city, killer. Tens of grams, region, kilogram, continental calamity. The universe probably won't throw this at us. But the scale tells us how much margin our atmosphere really gives and where it runs out. Next, we'll flip the question. If you wanted to stop or soften such an impact, what levers exist at all? Detection, diversion, deception, or is resilience on the ground the only sane answer? Can we stop or even soften a strike at 99.99% of light speed? The hard answer: you can't chase it. You must already be in the way. Warning time collapses to seconds. Anything that needs slewing, aiming, charging, or launching is off the table. Our only levers are upstream persistent sensing and downstream resilience on the ground. Sensing first. Surveys that find asteroids years out are great, but we also need all-sky, always-on watchers tuned for fast, bright events. Think geostationary optical sentinels that notice a daylight flash, wide field IR that catches the first hot plume, low-frequency radio arrays that hear the hiss of explosive ionization, particle arrays that flag a coherent air shower, and infrasound microphones that hear the pressure crack. Fuse those streams with lightning mappers and GNSS ionospheric monitors so operators get an automatic bright flash bulletin in under a second. Could we pre-place a shield? Spacecraft use Whipple shields. A thin bumper shatters a micrometeoroid, so a back wall absorbs a mist, not a bullet. Scaled to Earth, you imagine a sacrificial dust curtain in very high orbit, or at lone, a diffuse sheet that forces fragmentation far from the ground. Physics likes the principle. Logistics hate the numbers. You must lift colossal mass, maintain geometry against solar pressure and orbital tides, avoid creating debris, and keep navigation lanes clear. Even then, arrival angles are arbitrary. A global net would be required, not a patch over one continent. Magnetic armor sounds tempting. It fails for neutral matter. A net-charged projectile would still laugh at us. With gamma 70, P equals gamma mv is so large that R equals P2b is planetary even for strong fields. Earth's magnetosphere, tens of microtesla, is a feather against that punch. Electric fields and city plasma bubbles aren't better. You can't build a capacitor plate big enough or energize it fast enough to matter. Lasers and beams? Laser ablation works for slow asteroids because millimeters per second of delta V, applied for months, add up. At relativistic speed, there is no apply for months, and any ablation plume joins the projectile's momentum. Kinetic interceptors can't reach the meeting point. Nuclear standoff still needs distance you don't have. All classic deflection tools fail because time has been stolen. Could we thicken the atmosphere where it counts? In principle, you could seed the upper air with a global, ultra-thin aerosol to act like a planetary Whipple bumper. In practice, global is the budget. Killer, and anything dense enough to help, would degrade astronomy, satellite operations, and possibly climate. The cure becomes a daily harm. If we can't deflect, we manage consequences, translate physics into reflexes. For the public, if a clear sky flash is brighter than the sun, look away instantly. Don't go to windows, drop or cover eyes. Count the boom lags by seconds to tens of seconds, depending on distance. After the shock, expect falling glass. Use text messages. Keep voice lines free. Wait for official advisories. Treat it like lightning without thunder until the thunder arrives. For buildings, laminated glazing or safety film. Exterior shutters were common. Mechanical fasteners on facades and signage that resist suction and slap. Robust roof anchoring. For critical infrastructure, automatic grid reconfiguration to ride through fast faults and temporary ionospheric weirdness. Black start capability. Redundant comms that fall back to line-of-sight radio and satellite texting. For hospitals, surge plans akin to earthquake playbooks, lacerations from glass dominate. For aviation, give controllers and crews a checklist. A high-altitude airburst can impose rapid overpressure steps and glare. The reflex is similar to nuclear flash procedures. Avert eyes. Avoid abrupt control inputs during the initial shock. Verify pressurization. Then route around the expanding disturbance using pilot reports and space-based lightning feeds that will almost certainly flag the flash. Coasts deserve a note. A megaton-class airburst over water doesn't shove the ocean like a deep quake, but the traveling pressure wall can seed meteotsunami-like oscillations. Harbors and long, shallow shelves can amplify them. Sirens and signage should mention pressure-induced waves alongside storm, surge messaging in vulnerable areas. Science can help by trimming latency. Global networks already watch for infrasound and fast optical transients. Add cross triggers so a bright flash, auto-queries, particle arrays, and ionospheric sensors. Publish automatic, geolocated alerts when an air shower exceeds coherence thresholds, the signature of a compact, ultra-energetic initiator rather than a routine cosmic ray. Ionospheric flash bulletins from space. Weather centers would warn of brief regional HF and GPS distortion. There's also a forward-looking duty. Human technology is edging toward relativistic probes, laser-pushed sails, for example. If gram-scale craft ever cruise at significant fractions of C, we'll need strict traffic rules. Launch geometries that avoid Earth intercepts for centuries, self-disarm protocols, and transparent ephemerides so civil sensors track outbound beams and vehicles. The best way to avoid a man-made relativistic hazard is never to aim one at home. Preparing for a thunderclap you'll probably never hear still pays off. Better all-sky coverage improves wildfire detection, bolide tracking, and storm nowcasting. Hardened grids and comms help in heat waves, solar storms, and hurricanes. Window films and good messaging save eyes in ordinary meteor events. In risk management, low probability, high consequence scenarios ride in the same lifeboats as the disasters we know we'll face. So mitigation is brutally honest. You cannot swat a relativistic pebble the way you can nudge an asteroid. Your best move is to know a few seconds sooner. Keep people away from glass. Keep aircraft and grids in safe modes. And design cities that shrug off a fast slap of air. The planet already carries the only big shield we get, 100,000 tons of atmosphere above each city block. Our job is to let that shield work and be ready for the aftershock. Next, we'll rewind the physics tape and zoom into the microsecond sequence of the burst itself. How atoms tear, how the plasma grows, and how the shock self-organizes as the fireball rams the wind. That's where the images you can feel begin. Start at time 0, the first molecule the intruder meets. The object is still coherent, but its surface electrons are already being ripped away by the impossible ram pressure. In the projectile's frame, air is a sheet of matter crushing in at almost light speed. The first atomic layers ionize. Surging currents wrap the nose in a plasma sheath, opaque to most wavelengths and reflective to radio. 10 nanoseconds later, the nose is a welder's arc turned inside out. Collisions are so violent that electrons race to relativistic speeds inside the sheath. Bremsstrahlung X-rays spill out. A few photons are energetic enough to spawn electron-positron pairs. Most energy still goes into ripping molecules and heating ions, but a tiny fraction appears as a hard, prompt flash. By 100 nanoseconds, a bow shock has coalesced. Upstream air has no time to slip around. It is hammered, stalled, and driven sideways. Stagnation pressure at the cap is enormous, and density behind the shock leaps. A radiative precursor ultraviolet that outruns the hydrodynamic front preheats air still ahead of the blast by microseconds of travel. Set the distance scale. At 99.99% of C, the projectile covers 300 meters per microsecond. In that first microsecond, it both disassembles and plows through city blocks of air. That's why the trail is short. Energy arrives almost as a sheet, not a line. Between 100 nanoseconds and a microsecond, fragmentation takes over. This is explosion in flight, observed in NASA Ames ballistic range tests at far lower speeds. Once dynamic pressure exceeds material strength, a body shatters. The fragments present more area and the breakup accelerates. Here, the cascade is essentially instantaneous. The projectile turns into a spray of vapor, droplets, and hot plasma entrained in the forward rush. The newborn fireball is teardrop-shaped. A bright forward cap where deposition is fiercest, followed by a wake still overpressured and incandescent. Kelvin-Helmholtz billows ruffle the flanks where fast. Hot gas rubs cooler air. A toroidal vortex tries to roll up behind the cap, the same donut seen in underwater blasts stretched and dragged downrange by momentum. From 1 to 10 microseconds, the physics is a duel between radiation and motion. Radiation wants sphericity photons, heat, and push sideways. Momentum keeps the blast-pointed mass and velocity stay aligned. The compromise is a forward-leaning bubble whose shock is strongest slightly ahead of the path. Chemistry wakes up here. Ripped nitrogen and oxygen recombine in non-equilibrium fits. Ionized nitrogen radiates near 337 nanometers. Oxygen's triplet around 777 nanometers adds deep red. Sodium, if present, flashes near 589 nanometers. But at tens of thousands of Kelvin, the continuum from hot plasma dominates. Lines ride on a white core. 10 to 100 microseconds. The shock has sharpened into a hard shell. Inside, pressure is dozens of atmospheres. Outside, air is flung aside faster than sound can warn. The shell expands laterally at kilometers per second, even as the whole structure sprints forward. Vorticity wraps like rope around the bubble. Shear feeds eddies that later seed turbulence and cloud. At 100 microseconds to a millisecond, the body is gone. Only plasma and momentum remain. The bow shock decouples from the internal source and becomes a freer blast wave. Ultraviolet fades first. To the eye, a sun-bright white core with a halo cooling toward orange, then red. To microphones, the start of an N-wave, rapid rise, short plateau, slower return, sonic boom shape scaled up. In the same millisecond, the air shower matures. A hadronic core from nuclear spallation rides with the plume. Muons and high-energy electrons spear the ground far from the track. People don't notice, detectors do, registering a crisp, coherent burst, consistent with a compact initiator. A faint, bluish Cherenkov component may mix into the flash, but thermal glare buries it. 1 to 10 milliseconds. Hydrodynamics owns the stage. The blast wave does classical things, sweeping, compressing, heating while the bright cap still leans forward. The vortex ring stretches and sometimes pinches off, leaving a torus that rolls back into the wake. If dust or sea spray lies below, the pressure step lofts it into a skirt that flows outward as a dirty halo. 10 to 100 milliseconds. Geometry simplifies. Sphericity wins, As momentum bleeds into air, edges cool to incandescent orange. The core drops from white to lemon to gold. The pressure wave steepens into a crack. If you are tens of kilometers away, this is when your windows decide whether to fail. At a second and beyond, the bright heart is gone. Remaining light comes from hot cloud tops and recombination, afterglow oxygen green and red if high, amber dust if low. The ionized column disturbs radio like a wrinkled mirror. High-frequency links scatter, GPS solutions jitter, VHF and UHF bend. Within minutes, winds shred the plume into filaments that seed ripples at sunset. Across the sequence, the key number is energy per unit length, dE, dx, and it is ferocious here. Ordinary meteors deposit energy gradually. The relativistic intruder dumps it in a compressed column, so peak overpressures climb. That is why the hazard order is flash, shock, debris, then fire. The flash is first. The shock follows. Debris is what the shock turns everyday life into. Zoom once more into the first microsecond and name the stages engineers care about. Stage 1. Ionization and sheath formation, electromagnetic, radiative, messy. Stage 2. Structural failure and explosion, in. Flight mechanical, fragmenting, multiplicative. Stage 3. Blast self-organization, hydrodynamic, shock. Dominated, momentum, guided. This script is universal, only the font size changes with mass. When NASA, ESA, and university labs model this, they splice codes. Particle Monte Carlo for the initial collisions, radiation, hydrodynamics for the hot cap, and compressible CFD for the blast. The outputs guide utilities, pilots, and emergency managers. How fast the pressure front steps, how glare blooms, and how many seconds separate flash from boom at given ranges. Microseconds shape minutes. Minutes shape outcomes. Next, we'll lay those outputs over two maps, city and sea, and see how altitude shifts the footprint, the injuries, and the recovery when the sky breaks over concrete versus water. Lay two maps on the table, city and sea, and slide a clear ruler labeled burst altitude across both. Same speed, same energy, different outcomes. Altitude is the hidden knob that turns a terrifying flash into anything from a global news story to a local catastrophe. Case A. High stratosphere deposition, about 35-50 kilometers. Over a city, this is spectacle plus a slap. The sky goes white for a heartbeat. Shadows jump. Then a slow, rolling boom arrives. Ground overpressure is modest, except directly beneath the track. Most windows hold, though brittle panes and tired seals fail. The bigger effect is aloft, an ionized sheet that scrambles HF, bends VHF, and makes GPS jitter for minutes. Airliners near cloud tops get harsh glare, but ride through by procedure avert eyes, verify pressurization, monitor instruments. Street life starts again almost immediately. The main hazard is people who ran to the window at the flash. Over the ocean, the same high burst decorates satellite images, not coastlines. Ships feel one concussive thump and a lash of spindrift. The sea's skin roughens into a bright ring and fades. Coastal gauges might record centimeters of oscillation if the track runs parallel to shore, but harbors hardly notice. Recovery is just noticing. Case B. Mid-stratosphere to tropopause, about 18-30 kilometers. This is the dangerous band for cities. The shock hits the ground as a fast, sharp step. Urban canyons amplify reflections. Glass is the weak link. The life-saving rule is simple. People who run to windows get hurt. Laminated glazing and safety film act like seatbelts. Unprotected panes become knives. Clip in facade panels can pop. Roof skins peel at corners. Tall signage tears. The footprint is not circular. Momentum leans the hot cap forward. so downrange neighborhoods get a stronger shove than cross-range ones at the same radius. Expect a daylight bright flash, a 1 to 10 of seconds pause, then a crack that tips shelves and sprays shards. Power flickers as lines slap and substations trip. VHF and GPS wobble for a short while. Cell networks may congest as alarms and calls spike. For responders, minutes matter. First 5, halt trains. Slow freeways, push the message. Turn away from windows. Shelter from falling glass. Expect a delayed boom. Next 15. Open surge capacity for eye injuries and lacerations. Dispatch utility crews to isolate arcing feeders. Move ladder trucks to protect dense roof clusters if embers appear. Hospitals should think earthquake triage with fewer crush injuries and more cuts. Schools, malls, and transit hubs need glass sweep teams and cordons before people are released back into atriums and platforms. Case C, upper troposphere deposition, about 8-15 kilometers. Now the slap becomes a punch. Shorter air columns mean more of the energy is delivered where we live. The overpressure that merely popped glass in Case B can shove walls and buckle lightweight frames. Vehicles are nudged in lanes, garage doors and warehouse skins drum and fail. Outdoors, exposed skin can feel a thermal sting. Plastic rooftops and parched vegetation can spot. Ignite within a few kilometers of the track under dry wind. Power and comms hiccup harder. Fast faults ripple. Microwave backhauls phase, jitter, and some towers temporarily brown out. In the worst urban geometry, close burst, many facades the failure pattern looks like a broad belt of shattered glazing, peeled roofs, scattered signage, and pockets of roof fires that need quick knocks before winds turn embers into lines of flame. The sea tells the same 3 stories at different volumes. High-altitude flashes roughen the surface and pass. Mid-altitude bursts push a pressure wall across the ocean that seeds long, low oscillations meteotsunami behavior. These grow where geography conspires. Long shelves, V-shaped bays, and harbors with resonant periods near the incoming waves. The result is usually tens of centimeters, occasionally more, but harbors are nervous places. Ropes snap and hulls bang. Upper troposphere bursts over water, add spray, and a gusty pressure step that can briefly upset small craft and helicopters. Offshore platforms feel a shove and a rain of spindrift, but decks are battered. Not cratered, the energy still couples mostly to air, not the water column. Weather and time of day modulate harm. Low cloud can shield eyes from direct glare but also trap light, bathing streets in a diffuse white that kills contrast for a moment. Night bursts blind more drivers but start fewer roof fires. Dry, windy days turn ember-level ignitions into line fires along medians and fences. Humid days trade flames for a brief steam fog in the wake. Snow absorbs light but reflects heat. Deserts do the opposite. Zoom into a city block and watch the wave arrive. A street-facing curtain wall flexes. If laminated, it crazes, but holds. If brittle, it shatters and sprays inward. Blinds and window films are not decor here. They are PPE for buildings. Inside, acoustic tiles jump, sprinklers sway, dust billows from old ductwork. In the alley, loose signage becomes scrap. 30 seconds later, the echoes rattle again as reflections return from high rises and hills. Pedestrians who kept their backs to the flash fare best. Those who looked up at the white sky are picking slivers from eyelids and cheeks. Orientation matters. Because the hot cap carries momentum, the damage ellipse tilts along the track. If the intruder races west to east, the eastern suburbs get the harder shove. Stage resources accordingly. Heavier rescue and utility teams go downrange, not only under the zenith. What about subways, tunnels, and basements? Underground is good for both shock and flash. The hazard becomes ingress, egress, and ventilation. Brief power dips, stall escalators, and trap elevators. PA systems may glitch. The play is familiar. Earthquake, style head counts, stare, well marshals, battery lights. Metro control rooms should hold trains and check for debris blown into portals before restarting. Ports and offshore platforms sit at an awkward intersection of the city and sea maps. Cranes are sail area on stilts. They catch the pressure, step, and sway. Container stacks can topple if lashings are sloppy. On rigs, open flame is rare but never absent. Flash plus pressure is an audit of ignition control. The good news, most energy stays in air. Decks are punished, not punctured. After the roar comes the invisible phase. The ionized sheet perturbs radio for minutes. GPS and timing networks jitter. ATC reroutes around the scar like a thunderstorm. Nitrogen oxides spike along the path. High-altitude ozone dips regionally for days to weeks before chemistry unwinds. Over coasts, salt spray lofted into the boundary layer can dust neighborhoods downwind, browning leaves and corroding rails in the following days. None of this is fallout. It is chemistry and weather cleaning up after physics. Recovery has a cadence. Hour 01, treat cuts, check for fires. Isolate live wires. Keep people off shattered sidewalks. Hours 1-6. Restore power islands. Clear arterials. Assess schools and hospitals. Crane down loose signage. Days 1-3. Replace critical glazing on clinics, control towers, and data centers. Swap scorched roof membranes. Sweep shards from transit corridors. Week 1. Audit the grid for hidden damage. Recalibrate GNSS, dependent systems. Publish a walk back so everyone understands flash, boom, and after effects. The upside of mapping this is clarity. High bursts are global stories and local shrugs. Mid bursts are city-scale disasters dominated by glass and grid. Low bursts are regional crises where structures and ports join the casualty list. The lever you don't control, the altitude where the energy stops, decides which map you live on. Next, we'll put numbers on the shock and light themselves. Practical ranges for flash blindness, window breakage, and facade failure at different yields and altitudes, so you can picture footprints without a CFD lab. Numbers time, but with guardrails. We want practical footprints. How far the flash can blind, how far the shock breaks windows, and where facades start to fail. 3 knobs set the stage yield, burst altitude, and range, and 1 scaling law does most of the lifting. For airbursts, many effects follow cube, root scaling, so distances grow roughly with W, 1, 3, where W is the explosive yield equivalent. Altitude then tilts the footprint forward along the track. First, the shock. Engineers talk in overpressure. About 1 psi, 6.9 kPa. Breaks a lot of glass. 3 psi starts minor structural damage. 5 psi blows in robust glazing and weak walls. 10 plus psi buckles frames and knocks down light structures. Different source, same air and shock math. Translate to our ladder. Example 11.5 megatons, 1 G at 25 kilometers. Expect a long, thin damage ellipse under the path. The 1 psi belt reaches across a metropolis. Untreated panes facing the sky fail. The 3 psi belt is narrower downtown scale, and 5 psi sits in a core a few kilometers wide, worst downrange of the zenith. Laminated glass and safety film / injuries, captured curtain. Walls keep shards in place. Example 215 megatons, 10 G, 20 kilometers. Scale distances by 2.5, the cube, root of 15, 1.5. The 1 psi footprint becomes regional. Suburbs deep downrange report. Widespread window loss. 5 psi pushes to low double-digit kilometers. Unreinforced masonry cracks. Warehouse skins and roll-up doors fail across industrial belts. Example 3, 150 megatons, 100 G at 15 kilometers. Scale again by 5 versus Example 1. The 1 psi contour sprawls across counties and coasts. 3 to 5 psi reaches far into a metroplex. Cladding strips, billboards fly, and many roofs peel unless well anchored. The atmosphere still prevents cratering. Shock remains the main mechanical risk. Now, light flash, blindness, and burns. 2 truths tame the uncertainty. 1. Most harmful light arrives in the first second from the hot cap and shock, heated air. 2. A bright daytime sky shortens flash, blind distances compared to night. Using conservative brackets from airburst literature, here's a practical rule for clear line of sight. Daytime flash blindness, temporary, not retinal injury. For a 1.5 mount burst high in air, expect risk within tens of kilometers. Drivers looking toward the flash can be dazzled across a city. At night, the range grows beyond 100 kilometers. Multiply by W13 for larger yields. At 15 mount, daytime risk can reach 50, 70 kilometers. At 150 mount, 100 plus kilometers. Haze or low cloud shrinks ranges, terrain blocks them. Thermal discomfort and spot ignition. Near-track pedestrians can feel a skin sting within a few kilometers for 1.5 mount, farther for larger yields, especially in dry wind. Combustibles like dry thatch, loose wood shavings, or plastic membranes can spot ignite in the 5-10 kilometers band for 1.5 mount, proportionally farther for bigger bursts. Metallic roofs and tile fare better. Dark polymer roofs fare worse. Windows and facades in usable numbers. Take 1 psi as the glass hazard threshold for ordinary panes, and 3-5 psi for robust glazing and attachments. If a city films street-level glass, injuries plummet even when the 1 psi belt passes. If curtain walls retain broken panes, streets remain navigable. If not, expect millions of shards per block. Altitude steers footprints. At 40 kilometers, 15 mount leans toward glare and comms hiccups. 1 psi belt only nips brittle panes. At 25 kilometers, 1.5 psi reaches the ground beneath the track and downrange the classic broken glass belt. At 12 kilometers, strong overpressures reach neighborhoods, light structures, and signage fail in bands aligned with the path. A quick driver's guide beats equations. If a flash blooms brighter than the sun, avert your gaze, do not search for the source. Don't go to windows, count. If the boom arrives in under 5 seconds, you're close. Stay down and cover. If 10 to 30 seconds pass, you're farther. Stay away from glass until after the first crack and its echoes. Timing is physics. Sound lags light by 3.3 seconds per kilometer. Sea surfaces read the shock differently. A 1 psi step is subtle on open ocean. Ships feel a slap and a lashing of spray. Harbors and long shelves can amplify the pressure-forced wave, giving tens of centimeters in surges that part lines. Scale surges by yield, 1, 3, and by how well a harbor's natural period matches the wave geometry matters as much as energy. Put the brackets into a compact checklist. 1.5, mount at 25 kilometers, day flash, blindness, city scale, night beyond city. 1 psi metro wide, 3.5 psi downtown, industrial belts. Spot ignitions, few, kilometer band under track in dry wind. 15 mount at 20-25 kilometers. Multiply by 2.5, 1 psi regional, 3.5 psi across metroplex. Expect facade stripping and roof peel unless anchored. Temporary GPS, VHF wobble across a state-scale footprint. 150 and at 18 kilometers. Multiply by 5, 1 psi, multi-region. 3.5 psi, city to multi-city. Widespread cladding loss, signage down, spot fires more common. Strong infrasound circles the globe for days. Caveats keep us honest. Thermal fractions for kinetic airbursts are uncertain and depend on altitude and composition, so burn ranges can be smaller than nuclear charts suggest. Terrain, weather, and building standards reshape the map. Haze tames glare. Wet streets kill embers. Laminated glass turns a knife storm into a cleanup job. And the ellipse leans. Downrange takes the harder shove because the fireball keeps its momentum while it grows. These rules come from cube root scaling, facade and glazing tests, meteor physics, column models, and real events. Chelyabinsk for glass, injury patterns, and infrasound. NASA, ESA belied catalogs for deposition altitudes, global lightning and GNSS networks for flash plus ionosphere behavior. They're guides, not guarantees, but guides are exactly what you need in the seconds between white sky and crack. In short, yields set the scale, altitude sets the character, cube, root gives the estimate. If you remember nothing else, remember this: bright flash, look away, delayed boom, stay clear of glass. Next, we'll trace the origin story. What in the universe can even try to push matter this fast, and why macroscopic chunks almost never get a ride? Cosmic accelerators from supernova remnants to black hole jets, and the hard limits that protect us. Where could anything get this fast? The universe has engines, but they fling charges, not rocks. Real accelerators trade size for magnetism and time for chance. Their language is fields, shocks, and wandering particles that, step by step, steal energy from violent flows until a lucky few exit as winners. That makes ultra-relativistic bullets one proton or one nucleus at a time, not pebbles. Start with a shock. When a massive star dies, its debris slams into interstellar gas and sets up a supersonic, magnetized front. Charged particles ping-pong across that front, scattering on magnetic ripples. Each crossing adds a small percentage of energy. This diffusive shock acceleration is slow but ruthless. Enough crossings and energies soar. Telescopes see the fingerprints. X-ray images of young remnants show razor-thin rims where electrons radiate synchrotron light. Ground-based gamma-ray arrays catch hard spectra that reveal protons smashing into nearby gas and making pions. Put together, the data say supernova shocks can reach at least the knee of the cosmic ray spectrum, around a quadrillion electron volts, turning dead stars into neighborhood particle factories. Now turn the dial to 11. Black hole jets feed a supermassive black hole, and it launches twin, magnetically collimated fountains at relativistic speed. Inside those jets, live shocks, shearing layers, and magnetic reconnection sites, natural accelerators with stupendous voltage. Blazers jets aimed almost at us flare across the spectrum from radio to TV gamma rays. Every so often, a peta-electron-volt neutrino arrives from the same patch of sky, a smoking gun that protons were accelerated and then crashed into something. Gamma-ray bursts are even more violent for a few seconds, with outflows so fast that only a relativistic model explains the light curve. Pulsars and newborn magnetars add yet another engine, a spinning, ultra-magnetized conductor that behaves like a cosmic dynamo. All these machines obey a simple guardrail called the Hiller's criterion. Put magnetic field strength on one axis and accelerator size on the other. Draw a slanted line that says, to confine a particle of a given rigidity, you must be this big and this strong. Supernova shocks occupy one region, pulsar winds another, and active galaxy jets and GRB outflows higher up. To hold a proton at 10-20 eV, you need either a giant system with Gauss-level fields stretched over light years, or a compact engine with absurdly intense fields. The plot doesn't prove who does the job. It tells you who even could. Now ask the forbidden question. Could any of these engines throw a macroscopic clump dust, a pebble, a marble to 99.99% of light speed? Physics answers with several firm no's. No, because neutral matter doesn't listen to magnets. Shocks and jets work because charges feel fields and can be trapped long enough to take many energy steps. A neutral rock has no handle. You can ionize its surface and push on that charged skin, but then you're trying to accelerate a boulder by tugging a coat of paint. The charge-to-mass ratio collapses. Acceleration per unit field is tiny. No, because coupling tears the clump apart. Suppose you do charge the grain. The outer layers feel the push. The interior lags. Stresses build. The skin ablates, and the piece fractures. Jets are not gentle. Turbulent shear and grain. Grain collisions add hammer blows. Even at laboratory speeds of a few kilometers per second, dust grains shatter and vaporize on impact. In a jet moving at a good fraction of light speed, collisions are rarer but catastrophically more destructive. Solids do not remain solids long enough to be sped up coherently. No, because radiation cooks what fields cannot break. A clump racing through an intense photon bath near an accretion disk, inside a GRB fireball, or even through the thick starlight of a galactic core feels drag. Photons Doppler boost in the clump's frame. Inelastic scattering and absorption convert bulk motion into heat. Dust charges, sputters, and sublimates. Long before you reach gamma 70, the candidate becomes a mist of atoms. No, because the universe taxes the top end. Even lone protons above roughly 510-19 eV collide with the cosmic microwave background and bleed energy by making pions the Greisen, Zatsepin, Kuzmin effect. Their mean free path shrinks to tens of megaparsecs. Heavy nuclei photodisintegrate on the same photon bath. If single particles struggle to keep their winnings across intergalactic space, cohesive clumps have no chance. Every radiation field becomes a sandblaster. No, because gravity accelerates poorly without shredding. Imagine a rock falling toward a black hole, trading potential energy for speed. Tidal forces grow ferocious. Differential gravity rips extended bodies. Close enough to get a serious relativistic boost, the object is spaghettified and heated, not launched. Escape requires a rigid body and a coherent push. Black hole neighborhoods melt both assumptions. The universe does fling bullets, but their speeds tell the story. In young supernova remnants, you can trace knots of ejecta racing at thousands of kilometers per second fast for matter, but only a few % of C at most. In jets, you see bright blobs sprinting with apparent superluminal motion, an illusion from light-time effects. The true bulk speeds correspond to Lorentz factors of order 10, sometimes a few tens. Those blobs are magnetized plasma, not bricks, and their internal shear and radiation drain energy even while they race. What about light pressure? Lasers can push sails. Ambitious concepts aim to drive gram-scale craft to about 20% of light speed with multi-gigawatt arrays. That is already breathtaking, and it highlights the gap. To reach 99.99% C, the energy per gram explodes by orders of magnitude compared with 0.2 C, and the engineering headroom vanishes. The sail must reflect almost perfectly, keep alignment under staggering flux, and dump heat it has nowhere to radiate. Nature does not build such sails. Stellar radiation and supernova light push dust, but only to modest fractions of C. So where do the ultra-high energy messengers we do see come from? Probably a mixed roster. The shocks of GRB afterglows, the inner regions of blazar jets where magnetic reconnection lights up, perhaps the magnetospheres of newborn, millisecond magnetars acting as dynamo monsters. Each candidate fits somewhere on the Hillas plot and dodges different losses. We infer their presence from secondary light, TV, PV neutrinos, hard gamma rays, and the footprints cosmic rays leave when they crash into gas and dust. Notice the conspiracy in our favor. The cosmos can hand a single proton 10, 20 eV, but it struggles to give a handful of atoms a shared ride. Fields couple to charge, not to mass. Radiation whittles solids down. Collisions and shear finish the job. By the time any macroscopic piece tries to surf a relativistic engine, it has been turned into exactly what the engine wanted: charged particles. The thing that could have hit us as a paperclip is milled into ions long before it leaves the shop. That is why this scenario is both instructive and merciful. Ultra-relativistic impacts on Earth are terrific for learning because they force us to balance energy, momentum, and radiation honestly. They are merciful as risk because the universe's machines do not seem able to manufacture fast rocks. We still take the lesson. Nature can throw single particles at absurd energies, and our atmosphere handles them daily. But a true pebble at 99.99% C would demand an accelerator that grabs a neutral object without tearing it apart, and then protects it from radiation all the way home, something the cosmos, thankfully, does not appear to build. Next, we'll drop back into near-Earth space with a scientist's eye and a filmmaker's ear. How satellites, all-sky cameras, lightning mappers, and particle arrays would record a real relativistic airburst. And how those timelines stitch into a minute-by-minute story you can edit to music. Picture a clear Tuesday, late morning. Far above, geostationary weather satellites stare at Earth's disk. One pixel brightens like a camera flash, pure white for a heartbeat. That single square means the sky just went non-linear. Lightning mappers flag it, then hesitate. The pulse is too fast, too high, and far from any storm. Ground all-sky cameras echo the glare a fraction of a second later. 0 seconds. From orbit, the spike blooms and collapses in under a second, flooding visible and near-infrared channels. Automatic classifiers stamp lightning, then withdraw it when the signal sits above cloud tops and clear air. At street level, hard shadows jump and vanish. 2 seconds. Radio gets strange. HF links hiss. VHF and UHF skip in ways that don't match weather. GPS near the track loses sub-meter lock. Timing wobbles. Controllers shrug to procedure brief. Ionospheric ripples happen. The fix is patience. 3 to 10 seconds. The shock reaches the ground beneath the path and races outward. For people who looked away, a hard crack is followed by a rolling thump that bounds between buildings and hills. Glass is the chorus snaps, plinks, avalanches. Security cameras catch flags lashing and dust peeling from roofs. 30 seconds. Particle arrays speak. Muon counters and water Cherenkov tanks register a coherent burst, pancake thin rather than the usual drizzle of cosmic rays. Lightning networks see the bright optical transient, but no radiospherics of a strike. Meteor cameras report no streak, just an instant flare. The signature is turning specific. 1 minute. Weather centers issue internal notes. Large optical transient, non-convective, probable high, altitude energy deposition. Aviation desks forward the advisory. Crews flying in clear air admit the glare startled them. Those drilled on flash procedures looked away and checked pressurization. Air traffic control draws a soft reroute box around the scar. 5 minutes. Satellite loops show a growing fuzzy donut in upper air fields. Color composites hint at ionized nitrogen and oxygen recombining along the path. A pale halo that fades as winds shred it into streamers. Space weather desks merge feeds. Optical flash, radio scatter, GNSS scintillation, and a slab of infrasound rolling outward. 10 to 20 minutes. Emergency rooms near the footprint see what Chelyabinsk taught to expect. Eye cuts from glass, a few flash burns, sprains from falls taken during the boom. Utilities split grids into islands while they audit lines for nuisance trips and slapped conductors. City crews sweep intersections where glazing fell into the right-of-way. Incident commanders shift resources downrange because the damage ellipse leans with the track. 30 minutes. National infrasound arrays plot the expanding ring. Barographs trace the classic N wave. Seismometers ping from air to ground, coupling a low-frequency nudge riding down bedrock. Space weather centers post a short advisory, brief regional HF disruption and navigation jitter near the path, clearing within the hour. Mariners get a footnote. Harbors may slosh. 1 hour. Snapshots from different longitudes complete the picture. Thermospheric sensors see a ripple in electron content. GNSS analysts map a traveling ionospheric disturbance, marching off the track like a wake. Newsrooms run the sequence producers love: orbiting view of the flash, the high-altitude ring drifting, then street clips of rattling windows and stunned faces. Scientists keep public language careful. In private, they already name it a relativistic airburst initiated by a compact object. 4 hours. Recon flights and high-resolution satellites image the line. Overland, clues are subtle. Strips of broken glazing, peeled roof skins, scorched verges, and fields in a narrow band. Over water, the sea writes in texture a faint roughened ribbon already dissolving. Port authorities tally parted lines and bent fenders. Schedules snarl for a day, not a season. Day 1. Instrument teams triangulate. Timestamps from all sky cameras define planes that intersect in a line the track. Parallax between geostationary and polar orbiting platforms pins the altitude where energy dumped. Particle arrays compare timing across hundreds of kilometers. The coherence clinches a compact initiator rather than a meteor that fragmented over dozens of kilometers. Infrasound inversions backsolve a yield and a centerline by matching the observed spectrum to blast wave models. Days 2 to 5. Chemistry and weather finish the arc. Soundings and satellite spectrometers record a modest spike in nitrogen oxides where the flash ran hot. Regional ozone dips slightly, then heals. Aviation routes normalize. Inspectors walk the broken glass belt, and tick boxes laminated held. Brittle failed. Film helped. Utilities retired temporary islands and stitched the grid back to normal topology. Threaded together, those beats become an intelligible story. The lightning mapper says not lightning. The particle arrays say one coherent shower, not many small ones. The infrasound says big, fast, in the air. Satellite parallax says here, and this high. Together they spell the answer the sky wrote in a blink. What to make of it depends on where you stood. In downrange suburbs, you remember a white sky, a breath held, and a boom that set off a minute of little sounds. Glass, deciding whether to fail, signs creaking on their mounts, dogs barking at nothing. On the coast, quiet piers surged as if a long train had passed. In a cockpit, you averted your eyes and watched instruments ride through a brief glare. For the record, the planet passed the test it was built to take. Air acted as armor, turning kinetic fury into light, shock, and chemistry aloft. Networks made sense of it in layers: optical, radio, particles, pressure, each with its own delay, all converging by day's end. The next time the sky blinks, the choreography will be faster, because once a planet hears a new kind of thunder, it practices. The coda belongs to the numbers. Analysts publish the reconstructed yield with bars of uncertainty, the altitude band, the length of the deposition column, the footprint of one psi overpressure, and the magnitude of the ionospheric splash. Historians of instruments add a note. The same systems that catch lightning, track storms, and watch auroras solved a different puzzle without being told to expect it. The universe wrote a message at near light speed. We read it at human speed. Add nines and gravity listens. Add more nines and the universe files a noise complaint. That's the shape of relativistic scaling. 0.9 is fast. 0.999 is wild. 0.9999 is obscene. And 0.99999 is a different animal entirely. What changes isn't only speed, It's the Lorentz factor gamma and everything chained to it, kinetic energy, momentum, and how brutally the atmosphere turns motion into shock and light. Take 1 gram, because a gram keeps the head math clean. Rest mass energy, mc a quadrad, for 1 g is 910 u climbs, mc a quadrad. Kinetic energy is gamma mc a quad. At 0.9, gamma 2.294, gamma 27, 1.294, 1.1610, quarter J 27.7 kilotons. At 0.99, gamma 7.09, gamma minus 6.09, 5.4, 8 Chapern 10, Gwat, J 131 kilotons. At 0.999, gamma 22.37, gamma minus 1, 21.37, 1.92, Chevin 1016, J 0.46 megatons. At 0.9999, gamma 70.7, gamma 60, 9.7, 69.7, 6.2, 710 Tingu 60, 1.5 megatons. Same gram, 4 speeds, a 50-fold swing because gamma climbs like a cliff as you stack 9s. Momentum rides the same cliff, P equals gamma mv, gamma mc, at these speeds. For 1g at 0.9999 P binds 70.70.0001 chasing 3 bind seconds 2.1 chasing seconds 2.1 chasing seconds comparable to a 200-ton train car at 100 ms. Energy sets how hot and bright the blast gets. Momentum leans the blast forward and decides which suburbs take the harder shove. Altitude depends on areal density, m, a, for a sphere of radius, r, and density, rho, m, a, 4, rho, r, 3. Compared to the atmosphere's column mass, C910, 300 kilogram s squared, about 10 meters of water. A rock marble R equals 0.5 centimeters, Robanus 3000 kg m op spike, has m a 20 kg m a quadrad, tiny versus s, it dies high. A fist-sized stone, R equals 5 centimeters, gives 200 kilograms, m quadrad, still small. Meter-class boulders approach thousands of kg, m quadrad, but fragmentation slashes their effective areal density almost immediately. The fast rule: the sky wins by shredding, then coupling to the shreds. Composition helps less than you hope. Steel, rock, ice at tens of thousands of Kelvin, everything is plasma. Material strength matters for microseconds. Cross-section rules. Present more area and you couple harder. Fragment and your area explodes. Coupling spikes, breakup accelerates. It's a feedback loop that turns coherent motion into a short, brutal energy dump. Myth 1. Fallout and EMP. There's no chain reaction. Radiation is mostly thermal light with a little hard X-ray, gamma from bremsstrahlung, and pair production in the hot cap. Ground dose is small away from the core because air soaks it. Brief radio weirdness, HF scatter, GPS scintillation, comes from the ionized sheet behaving like a wrinkled mirror, not a classic nuclear EMP. Myth 2. The magnetosphere will bend it. Magnetic fields steer charges, not neutral rocks. Even a highly charged projectile barely curves in Earth's 50 mild place field at gamma 70. The only big shield you own is air, and, happily, it's excellent. Chemistry and climate sit in the noticeable, not apocalyptic lane for gram to kilogram shots. The flash rips N-dos and O-dos, knocks spikes along the path. Ozone dips regionally for days to weeks, then heals as winds mix and sunlight runs its cycle. There's no Pinatubo-style global dimming because you don't inject sulfate aerosols. Think short. lived upper air chemistry plus local smoke if roofs or fields ignite. Context calms the imagination. Chelyabinsk, 2013. A 20 m stony body at ordinary speed, hundreds of kilotons, long breakup path glass shattered across a city, 1,500 injuries, almost all from shards. Tsar Bomba, 1,961, 50 megatons, burst at 4 kilometers, no crater, but enormous window damage far away in a sparse Arctic setting, a lesson in air coupling. Pinatubo, 1,991, stratospheric aerosols cooled the globe, 0.5 degrees for a year or two. Our kinetic burst doesn't load the stratosphere with reflectors, so climate impacts are far smaller. Scale mass at fixed speed and the picture widens. At 0.99999, 10 G yields, 15 mount, 100 G, 150 mount, 1 kg, 1.5 gt. Altitude slides lower because the projectile survives a hair longer, but the mode stays airburst. Footprints grow from metro to regional to continental, dominated by 1.5 psi belts and a forward-tilted damage ellipse. Over ocean, expect harbor slosh and roughened seas, not basin-wide tsunamis. Trade speed against mass, and you see why adding nines is the scary lever. A 10G intruder at 0.9 c, 280 kT, is Chelyabinsk class. The same mass at 0.9999 seek, 15 mount, jumps 2 orders of magnitude. Mass buys linear gain, nines by cliff. Face gain, nature and engineering both struggle to add nines. Angle matters last. A shallow, skimming trajectory spreads energy over a longer ground track and leans the shock farther downrange. A steep one localizes the footprint near the zenith. Either way, the ground rule for people stays unchanged. Bright flash, look away. Delayed boom, stay off glass. If you want a pocket cheat card, keep these. Energy per gram, 28 kT at 0.9. 1.5 mount at 0.99999. Momentum per gram at 0.9999. 2 Chabantenschicht and slashed. Steering the blast forward. Altitude compare Ma to C. 10, 300 kilograms quadrad. Fragmentation erases high Ma fast. No fallout, no classic EMP. Expect brief radio, GPS hiccups, and an infrasound ring that walks the globe. Add nines and the sky stops being a place and becomes a process. That's why a sand grain can be a weapon and a paperclip can be a city-scale event. Next, we'll flip the near-miss case. A graze that deposits little energy, the faint auroral streak it can paint, and why the difference between hit and skim is the difference between a headline and a footnote. Imagine the same intruder, same terrifying speed, but luckier geometry. Instead of diving, it kisses the planet, skimming the thin air above the mesopause and sliding back to space. A near miss at 99.99% of light speed isn't silent, but it's closer to an aurora than an earthquake. The difference between hit and skim is column density, how much air the object plows through before escape. If the path integrates very little air, only a sliver of the kinetic energy couples, and the signature is light, not shock. Set the stage at 95, 130 kilometers altitude, where meteors begin to glow and the upper atmosphere shifts into an electrically tricky plasma. Up there, a relativistic grazer still shreds, no material survives the ram pressure. But because the air is orders of magnitude thinner than at jet height, the fragments and plasma spray race into near vacuum, and the blast can't build a hard, ground-reaching shock. Energy is deposited as ionization along a razor-thin line, not as a compact fireball. To an observer under dark skies, the signature would be a blade of light drawn across the stars in a fraction of a second too fast to track, a greenish afterimage lingering, That color betrays altitude and chemistry. At 9,120 kilometers, oxygen's 557.7 nm line. The classic auroral green can flare as atoms recombine. Nitrogen bands add violet edges. If the graze rides higher, into 180, 250 km, oxygen 630 mm red joins the show. It looks like a narrow auroral scratch that fades in tens of seconds. Instruments are better witnesses. Geostationary weather satellites record a sub-second white spike, then a faint smudge. All sky cameras capture a needle-straight arc that slowly diffuses. Coherent scatter radars, e.g. SuperDARN, reflect from fresh plasma irregularities. Ionosondes report a sudden, local jump. GNSS networks map a traveling ionospheric disturbance like a wake. Infrasound is barely there. At 100 kilometers, acoustic coupling to the ground is poor. What little reaches the surface is a soft, low-frequency sigh, not a crack. Seismometers stay quiet, that ordering light, radio, plasma first. Air last is the calling card of a skim. Numbers make small concrete. Take a 1 milligram speck at 0.9999. A full stop in dense air would dump 1.5 kilotons equivalent. In a true graze, the integrated air column can be 1,000 pounds, smaller than a dive, so only 1% to 0.1% couples before fragments escape. Roughly 15 tons to 1.5 tons of TNT, equivalent spread along a 100-kilometer ribbon at 100 kilometers altitude. That's plenty to paint the sky, too little to rattle windows. Could it skip like a stone? Not really. Stones skip because water is dense and delivers lift at shallow angles. Air at 100 kilometers is too thin to provide coherent lift to an object that is disintegrating as it moves. You might get a tiny upward bend of the centerline if ablation is asymmetric, more heating below than above, but momentum at gamma 70 keeps the path essentially straight. Think brushstroke, not bounce. A graze is kinder to satellites than a dive, but not entirely benign. Low Earth orbit spacecraft that cross the fresh trail minutes later could see odd drag and radio scatter as they slice through the cooling plasma. Most vehicles won't notice. The wake diffuses in tens of seconds to minutes, and orbits are sparse. Radio occultation experiments may misread the transient as weather until timing and geometry give it away. Geomagnetic context adds personality. In quiet conditions, the trail spreads diffusively, smearing into a faint ribbon steered by wind shear. During geomagnetic activity, field-aligned currents can grab the seed electrons and stretch the glow along magnetic lines, turning a straight scratch into a hooked filament. Think shuttle plume auroras and deliberate barium releases. Different causes. Same way fresh ions get painted by currents. From a storytelling angle, the contrast is clean. A hit is visceral flash, silence, then a punch of air and a chorus of glass. A skim is a sky event, spectral lines, drifting glows, radar echoes, scientists swapping excited emails. One fills trauma bays, the other fills preprint servers. One writes a damage ellipse on maps, the other draws a straight line on star charts. Detection pipelines should learn both dialects. Fast optical trigger, ionosphere check, radar cross-query, particle coincidence can classify a graze fast. Add automatic advisories to pilots and observatories. Transient auroral streak, non-meteor, non-lightning brief, GPS scintillation along track. Visual impact minimal. Amateur meteor and aurora networks supply ground truth. Phone clips of a blink, then a pencil, thin green, that oozes away. Could a skim ever turn into a surprise punch? Only if the track kinks into thicker air, say. A fragment dips under differential drag. At gamma 70, momentum is so huge that air can't bend the path quickly. The likely outcome stays what geometry promised. A brush, not a blow. The most human question is, would I notice? If you were outside at night and looking near the right spot, maybe a white blink, a faint green line, a vague itch on your radio. Indoors, you'd miss everything. Your devices would notice for you tiny timing hiccups, a little noise, a short-lived glitch on satellite links. By morning, a montage of instruments would tell the tale you never saw. And because the universe loves edge cases, the same physics that terrifies also protects. Making a macroscopic object fast enough to matter is fantastically hard. Making it also hit at the exact geometry that maximizes damage is harder still. Most such visitors, if they ever appear, will be skims, brief, beautiful, and destined for the upper atmosphere oddities folder, not disaster. So the difference between headline and footnote reduces to a simple product: density times distance. Multiply big and the sky punches. Multiply small and the sky writes in light. Our job as observers and storytellers is to read both kinds of handwriting. Next, we'll step to technology's edge. Laser-driven microsails at relativistic speed, the traffic code near Earth they would demand, and how to make sure our own probes never become the very hazard we fear. Start with the dream, a postage stamp film of glass and carbon, polished to near-perfect reflectivity, rides a river of light. On the ground, a phased array the size of a city locks a beam onto that sail and pumps momentum into it for minutes. No propellant, no tank. Just photons pushing until a gram of hardware reaches a fifth of light speed and slips into interstellar night. That dream has real sketches on real whiteboards. Laboratory sails have unfurled under lamps and lasers. Solar sails have flown and tacked on reflected sunlight. The missing piece is scale, an array powerful enough to push Gram-class craft to relativistic speeds, and a sail that can survive the flood of light without wrinkling, tearing, or boiling away. Engineers talk in reflectivity, emissivity, and areal density. If the sail reflects almost everything and radiates heat like a black cat in moonlight, it can ride the beam without turning into a crisp. If it can hold shape under nanometer-level pressure ripples from the phased array, it can stay centered in the river instead of surfing off the edge. Now fold the dream into risk. A gram at 0.2 C carries more energy than you think. Gamma at 0.2 C is about 1.0206, so gamma minus 1 minus C a quadrad for 1 gram is roughly 1.9 cm, joules around 4/10 of a kiloton. 10 grams at the same speed, a few kilotons. Those numbers are small compared with our earlier monsters, but they are not small near cities or satellites. If humanity ever builds a beam that can throw flecks at 0.2 C, it inherits the duty to make sure none of those flecks ever come back through Earth's sky. Write the first rule of a relativistic traffic code: never aim home. Launch geometries must be arranged so that even if a sail fails at t+1 second, the piece lives on a trajectory that misses Earth for centuries. In practice, that means an out-of-ecliptic aim with a safety margin tip the beam several degrees above the plane of the planets and bias the velocity vector outward so the path is hyperbolic with respect to the Sun, not a long ellipse that revisits the inner system. Error budgets have to be honest. If your pointing, phasing, and sail stability combine to give a worst-case 1 sigma of theta, you don't clear the shot with a safety cone of theta. You clear it with a cone several theta wide and still miss every planet's future position by millions of kilometers. The second rule is public ephemerides. Every launched probe gets a broadcast identity, a laser-rangeable corner reflector or retro tag, and an open machine-readable trajectory file from the minute the beam shuts off. Civil radars, optical trackers, and deep space networks should be able to cross-check where each sail is and where it is going. Silence should be suspicious. If a sail goes dark, its last vector and a conservative scattering model get published so observatories can keep it honest. Third rule: fail safe by physics, not policy. If the sail tears, it should tumble into a draggy posture that maximizes radiation pressure braking rather than sharpening into a dart. If onboard microelectronics latch up, the default state should vent or jettison reflective area, not preserve it. If an onboard lasercom fails, the sail should flip to a specular mode that makes it easier for ground stations to see and harder for the beam to couple further momentum. Fourth, beam hygiene. A multi-gigawatt phased array is its own hazard if misused. The facility's logic must enforce hard geofences, no lobe or side lobe that can cross Earth, the Moon, or any protected line of sight while energized. Beam windows must be scheduled around satellites and aircraft with automation and human veto both required. In the event of a loss of phasing or tracking lock, the array should defocus to a safe pattern in microseconds fail open, not fail tight. Independent watchdog scopes watching the main lobe from the side should kill the beam if they see energy where none should be. Fifth, rehearsal at kinder speeds. Before anyone throws a gram to 0.2 C, the same beam and sail designs should earn a boring resume at tens of kilometers per second. That campaign will surface all the mundane ways a sail can misbehave: wrinkling modes, thermal runaways at tiny hotspots, spin axis drifts that grow under beam jitter, photon pressure torques that amplify rather than damp, attitude actuators, micro gimbals in the payload, photon thruster patches on the sail, or clever diffraction gratings that steer without mass must show they can hold the beam's bright spot on center for minutes, not seconds. Sixth, don't count on luck for deconfliction. Low Earth orbit is messy. Cislunar space is getting busier. Deep space cruise corridors already host probes. A relativistic microsail won't hit anything in LEO. The speed, gulf, and geometry prevent it, but the beam that launches it can blind, cook, or confuse if carelessly pointed. That's why beam time should be global notified like rocket launches, with civil agencies and observatories in the loop, and a public no illuminate list that includes astronomical targets, crewed vehicles, and radio quiet zones. Seventh, test the universe's patience on the ground. Arrays should be sited where dry air, high altitude, and clear skies cut scattering and glare, and where a mispointed beam burns nothing alive. Closed-loop simulators that ingest real wavefront sensor data and real sail metrology should run red team scenarios: gusts, thermal plumes, a stuck phase tile, lightning, induced noise, a firmware bug that flips a sign. The kill chain should be physical: shutters, breakers, and beam dumps that trip when software or humans stall. What happens if, despite rules, a launched sail arcs back toward the inner system years later? The defense is geometry again. Out-of-plane launches make later intersections with Earth vanishingly unlikely. If a piece does drift inward, its area-to-mass ratio will be high. Sunlight and the pointing, Robertson drag will nudge it gently and predictably. It will not retain a knife edge at 0.2 C. Collisions with dust and photons will sand it down long before re-encounter. If tracking shows a non-zero Earth impact probability decades out, classic deflection tools work because the object will be moving at ordinary solar system speeds by then. Millimeters per second of delta V, applied years in advance, are enough. There is also a softer safety layer: culture. A relativistic beam is too consequential for a single lab or nation to treat as a private toy. Think air traffic control, launch range safety, and nuclear command fused into a new discipline: joint oversight, redundant sensors, command by consent, and a paper trail any auditor can follow. Think published hazard analyses and post-shot reports. You don't keep trust with secrecy. You keep it by being boringly transparent about how you remove single points of failure. All of this sounds heavy for a postage stamp, and it is, but the payoff is enormous. A trained beam can throw 1,000 tiny scouts toward nearby stars in a decade, each with a wafer camera and a magnetometer and a laser comm in its eyelashes. Those Gram-class scouts come with the ultimate safety feature. They are too small and too fast to be retargeted as weapons once they're gone. The true hazard window is at launch. Nail that, and the rest of the mission is curiosity on a needle. The narrative circle closes here. Nature probably can't throw a pebble at us at 0.9999 C, but we might someday throw a fleck out at 0.2 C. If we do, the beam that lights its way must be surrounded by a new kind of range, safety, and the sail must be designed to fail beautifully. Done right, the only thing our probes will hit at relativistic speed is interstellar dust, and the only thunder they'll leave at home is applause when the first images arrive. Let's slow down and tell this story the simple way so anyone can picture it without equations. Start with the headline. At 99.99% of light speed, even a tiny thing hits like a giant. Why? Because speed turns into energy. Think of rain. A light drizzle taps your hand. Now imagine those drops arriving fast enough to dent metal. Same drop, different speed, totally different punch. Near light speed, a grain of sand carries city-size energy. That's the part to remember. Small can be huge if it's almost as fast as light. What would you see and feel first? A sky-wide flash brighter than the sun for a blink. Then a pause. Your ears wait. Seconds later, the pressure wave arrives like a door slamming the whole world at once. Windows are the weak point, not because the air is poisonous or radioactive, but because glass hates sudden pushes. The safest reflex is simple. Look away from the flash, step back from windows, and wait for the boom. Why does the atmosphere help so much? Picture Earth wearing a giant air mattress. Above each square meter of ground sits about 10 tons of air. That mass turns a bullet into a mist. The fast object rams the air, shreds, and dumps its energy up high. Instead of a crater, we get a burst in the sky, light, heat, and a shock wave that spreads out and weakens as it travels. The air mattress saves the ground, even if it gives the city a harsh slap. What about magnets? Does our magnetic field protect us? Only against charged particles, like the ones the sun throws at us. Neutral stuff, rock, ice, metal, doesn't care about magnets. So the magnetosphere is a good shield for space weather. But the atmosphere is the hero against fast, solid things. Will there be radiation like a nuclear blast? No chain reaction. No fallout. The flash includes some X-rays and gamma rays from superhot plasma, but air absorbs most of it high up. On the ground, the hazards are old-fashioned. Bright light, loud shock, flying glass, and small fires on very dry days. Radios and GPS can act funny for a few minutes because the ionized air scatters signals. Could this trigger tsunamis over the ocean? Not the classic kind. The burst happens in air, so most energy stays in the sky. Ships might feel a slap. Some harbors can slosh if their shape amplifies the pressure wave, but you don't move deep water the way an earthquake does. If the sea behaves oddly a minute after a huge sky flash, step higher as a precaution. Then it's usually back to normal. How big is big in human terms? A 1-gram object at this speed paperclip mass packs energy like a large thermonuclear weapon. 10 grams is bigger still. A kilogram becomes continental news. But altitude matters. High in the stratosphere is mostly a light show and a rumble. Lower near jet height, the shock gets mean and glass becomes shrapnel. Same energy, lower burst, more harm. So what should people actually do if the sky flashes? Plain language checklist. 1. Do not stare. 2. Move away from windows. 3. Wait for the boom. It can lag by several seconds. 4. When the shock passes, check for small fires and injured neighbors. 5. Expect phone networks to be busy. Use texts if you can. What about airplanes? Crews already trained for bright flashes and weird radio. The drill is simple. Avert eyes, check pressurization, ride the initial bump, and route around the disturbed air. This isn't a hole in the sky. It's a hot patch that cools in minutes. Flights may detour the way they do around storms. Could this ever happen without warning? Yes. Our telescopes find slow movers weeks to years in advance and keep improving. But an object this fast gives almost no time. That's why the best protection is not last-second heroics. It's strong buildings, laminated glass, clear messages, and networks that automatically connect the dots from too bright flash to don't go to the window. Where in the universe could something get this fast? Nature excels at pushing single particles, protons, and nuclei to ridiculous energies in supernova shocks and black hole jets. But getting a pebble to that speed is hard. Magnetic fields push charges, not neutral rocks. Intense light cooks solids. Collisions in those places break clumps into dust and ions long before they reach near light speed. That's a quiet comfort hiding in the physics. A few quick what-ifs. Night, more people see the flash. Drivers can be dazzled. The rule, look away and don't rush to windows, matters even more. Cloudy, low cloud spreads the light and softens glare, but the shock still arrives. Underground or in a subway, good flash and shock are smaller there. Wait for power to settle and follow staff instructions. What would the aftermath look like in a city? A belt of broken windows under and slightly downrange of the track. Some peeled roofs and fallen signs in the hardest hit zones. Pockets of small fires where heat found the wrong material. A short-lived bruise in the ionosphere that made radios cranky. By day's end, a replay reel on the news. The orbital flash, the fading ring in the upper air, and street videos of curtains breathing in and out. The deep lesson is not fear, it's scale. The closer something gets to light speed, the more each extra 9 multiplies the stakes. A small thing can act big. But the same physics also gives mercy. The air above us is thick enough to turn a cosmic bullet into a skyburst, and the universe doesn't seem to build machines that throw stones at near light speed. We prepare for the rare case by doing things that help every day anyway: safer glass, smarter grids, clear advice. So if the sky ever blinks white, look away, step back, count, and help. The planet will do the heavy lifting. The rest is seconds of calm. Let's compare our nightmare to the loudest skies we've already lived, through real events that left glass on floors, rings in the ionosphere, and lessons in our pockets. Start with a familiar name: Chelyabinsk, 2013. A stony object about 20 meters across entered at ordinary cosmic speed, around 19 kilometers, fragmented along a long path, and exploded with a few hundred kilotons equivalent. It burst roughly 30 kilometers, and the shock broke windows across the city. Over 1,000 people were injured, mostly by glass. Why bring this up? Because it proves 2 points that carry straight into our near light speed story. 1. Airbursts aim their harm at glass and loose facades. 2. Simple instructions: don't go to the window after a bright flash, save eyes. Roll back to Tunguska, 1908. A few tens of meters of icy, rocky material detonated over Siberia and flattened trees across 20 square kilometers. No crater, the atmosphere did the stopping. Reports mention a skywide glow, a delayed boom, and a pressure wave that knocked people down at distance. Again, same anatomy. Air is armor. Shock does the work, and the ground is spared a crater even when energy is huge. Now cross over to controlled blasts. During the atmospheric test era, we learn the language of overpressure. 1 psi breaks a lot of glass, 3 to 5 psi damage light structures, 10 psi topples weak buildings. Window films and laminated panes reduce injuries. Roofs peel if corners aren't anchored. Signs and cladding that rely on suction cups and short screws go first. All of that generalizes. A relativistic airburst isn't nuclear, but it speaks fluent shock. What about light and radio? Thunderstorms taught us to watch the sky with more than eyes. We now have lightning mappers in geostationary orbit that notice fast optical flashes even in daylight. On the ground, amateur all-sky cameras see meteors and bolides every clear night. Radio amateurs and pros watch the ionosphere by tracking how radio waves bend and skip. After Chelyabinsk, analysts could reconstruct the trajectory from videos and infrasound alone. Today, the toolset is richer. Weather satellites, lightning sensors, GNSS timing networks, and infrasound microphones would stitch a relativistic flash timeline in minutes. We've also seen air makes glow, events that weren't meteors. The space shuttle's re-entry plumes and scientific barium releases painted artificial auroras that drifted and twisted along magnetic field lines. Those teach us what a high-altitude graze might look like. A narrow, bright scratch softening into green and red as oxygen and nitrogen recombine. They also remind us that the ionosphere is a mirror that sometimes ripples. GPS and HF hiccups are a feature, not a failure. Ocean lessons? Look to meteotsunamis, harbor surges driven by fast air pressure steps from squall lines and derecos. Ports have learned that a sharp, moving pressure bump can slosh basins that have the wrong natural period. Translate that: a megaton class skyburst over water won't drive a basin-wide tsunami, but it can ring certain harbors like a bell. Mooring lines snap, hulls tap fenders, schedules slip a day. It's trouble, not tragedy. Air safety playbooks are already written, too. Pilots train to avert their eyes from unexpected flashes, ride through pressure bumps without over-controlling, and check instruments when radios get weird. Controllers have reroute muscles from volcanic ash, wildfires, and thunderstorms. A relativistic airburst is a new cause, not a new type of disruption. Public risk communication, again. Chelyabinsk is the teacher. Most injuries came from people who walked to windows after the flash and stood there when the shock arrived. Towns that later adopted flash, turn away, wait for the boom, as a lightning rule cut glass injuries in later bolide events. Window film helped, too. Small, boring upgrades beat big, exotic gear. Detection networks aren't just space toys. The CTBTO's infrasound array, built to monitor nuclear tests, hears large meteor airbursts and maps their energy. GNSS networks were created for navigation, yet they reveal traveling ionospheric disturbances from rocket launches, quakes, and meteor trails. Weather satellites watch clouds, but they also catch the white spike of a bolide. Redundancy is our friend. Different sensors with different blind spots converge on truth. Even city infrastructure has had dress rehearsals. Earthquakes and hurricanes taught utilities to island grids, hospitals to triage cuts and crush injuries, and city crews to sweep glass from transit corridors fast. Swap crush for more glass, more burns, and you've got the playbook for a mid-altitude airburst day. Data centers and control towers now spec laminated glazing. Telecoms practice congestion control. Broadcast stations can push cell phone, look away, messages almost instantly. What about chemistry and climate? Volcanic eruptions injected sulfate and cooled the globe for a year or two. Rocket exhausts and re-entry plumes sometimes leave brief ozone scars. Large meteor airbursts spike NOx and dent ozone locally for days to weeks. That's the honest bracket for relativistic airbursts. Noticeable, not civilization level. It's a sky bruise, not a winter. Last, cultural memory. Humans are good at forgetting rare risks until a neighbor posts a video. The remedy is rhythm. Annual meteor showers as teachable moments. School drills that tuck "don't go to the window after a flash" alongside "don't stand in doorways during quakes." Public service clips that translate sound lags light by 3 seconds per kilometer into, if you count to 9, the boom will be here. Practice makes reflex. So the nearest neighbors to our scenario, Chelyabinsk, Tunguska, nuclear test data, meteotsunami surges, shuttle plumes already sketched the map. Air is armor. Glass is a knife if you treat it wrong, and a shield if you treat it right. Sensors you already paid for will tell the story in layers. And the fixes that matter most are neither secret nor expensive. Laminated glass, anchored roofs, clear messages, and networks that talk to each other without a committee. The comfort in all this is double. First, the universe is stingy about making fast rocks. Second, even if one arrived, we've accidentally trained for the day. Storms taught us the sensors. Quakes taught us the grid. Meteors taught us the glass. We're better at this than we think. Picture an ordinary Wednesday clear air, good visibility, a breeze that barely moves the trees. We'll tell the story in 4 voices, so anyone can wear it for a minute and understand what to do when the sky goes white. The street. You are walking out of a coffee shop with a paper cup and your phone in your other hand. The light changes. Not brighter like noon arriving, whiter like someone opened a door to a studio. Your shadow sharpens and jumps. Every instinct says, look up, don't. You turn your head, blink, and face the brick wall. The coffee lid shivers. Somewhere far off, a dog barks. Then another. You count. 1, 2, 3. The boom arrives like a door slammed by a giant. Air pushes, then pulls. The shop windows thump. A few panes crack with a sound like ice in a glass. A gust of dust flows along the sidewalk as if the city exhaled. You keep your eyes down and step away from the glass front. A heartbeat later, the second sound arrives, falling glitter. It's the little shards from a cheap pane that didn't have safety film. People who rush to see the flash stand frozen in place, hands over eyes, friends pulling them back. You say the world's shortest safety speech to the stranger next to you, don't go to the window, and it feels strangely important because now you both own the moment. Traffic slows. Some cars have pulled to the curb. Others keep rolling, startled but steady. Above, the sky looks normal again except for a thin smear, the way contrails look when a plane turns but faster, higher, too straight. Your phone signal is jittery for a minute. Texts eventually go through. By the time you look back at the shop, the staff are taping a crack with painter's tape and sweeping glitter into a pan. 2. The cockpit. You are at FL 360, clear of cloud, 10 minutes from top of descent. A square of the world goes white. Your training does the work. You avert your gaze, eyes to the panel, and you say the words you practice for lightning. Flash avert. Cabin and pressurization steady. The glare falls away like you passed a bright billboard. The radio gets scratchy. A VHF handoff repeats. Your FO trims a click and calls ATC. We just had a bright flash. Brief comms, distortion, maintaining. Center is already on it. Reroutes are drawing around a scar that looks like a storm cell with no rain. You're not spooked, exactly. You've ridden through volcanic ash reroutes, wildfire plumes, noctilucent clouds that made the horizon look wrong. This is just a new page in the same book. 10 minutes later, the scratch is gone. An operations message arrives. Transient upper atmosphere ionization event. Expect GPS scintillation near track. For 30-60 men. Your passengers never knew the name for what they saw. You know enough to keep it boring. 3. The harbor. You are a port dispatcher on the morning shift. The flash makes the cranes into silhouettes, like a photograph taken without warning. 4 seconds later, the windows in the old admin building tick, nothing more. Your barograph bought during the last big squall after a minor meteotsunami made the boat's shuffle draws a neat step, like a staircase drawn by an engineer. You key the VHF and say, Harbor Advisory, Briefs H possible, secure lines, stand off bollards. 2 tugs answer. The pilings take a slow breath. A line snaps in the North Basin, bad knot, wrong angle, and a bosun swears in a language you don't speak. You're not frightened. You're busy. 30 minutes later, the water is its old self, and the group chat is full of theories. You forward the national notice that just came in. Non-convective optical transient. No tsunami hazard. Expect minor harbor oscillations. You highlight minor. Your people are good at reading what's not bolded. IV. The sky room. You are a scientist in a windowless floor with maps on every wall, and your day turns into a choir. The GOES loop shows 1 pixel saturate for a fraction of a second, then the ghost of a ring that drifts and smears along the wind. The lightning mapper shouts, then corrects itself. Not lightning. The all-sky camera at a university 300 kilometers away sees a room, bright, blink. The next frame shows a narrow smear that already looks less white than your memory wants it to be. GNSS plots bloom with a traveling ionospheric disturbance marching like a ripple on a pond. The infrasound network shows circles expanding, time-stamped like tree rings. You have playbooks for this. You call the aviation desk with plain language. Bright flash. High. Expect brief GPS noise. No ash. No weather. Advise crews. Flash procedures only. You type the sentence you practiced and secretly hoped to never use. Probable relativistic airburst. Yield estimate pending. Cut back to the street. The stranger you warn not to go to the window thanks you. It feels awkward to be thanked for something so small, but that's the whole point. The big physics is upstream and done. The small human physics is what's left. Someone shouts that a planter is smoking where a plastic tarp caught a glare, and you help kick dirt onto it. It's mundane and useful. The city breathes. The first news hits a few minutes later, then better versions an hour after. In between, the internet invents theories. You ignore them and pay attention to the people with timestamps and coordinates. The same satellites that watch hurricanes caught the flash. The same sensors that trace lightning saw the shape and crossed it off. The same microphones that listen for nuclear tests heard the boom roll around the planet. The same GPS that guides your rideshare noticed a wrinkle and ironed it out. By afternoon, the pattern is clear. The broken glass belt runs under and downrange of the zenith. The shock arrived fast enough to be one event, not thunder. The thermal sting said a few dumb things: smoking plastic roofs, dry mulch, a heap of pallets, nothing like a citywide fire. Hospitals report eye cuts and a handful of flash burns. The triage nurse says it looks like a storm without wind. The utility posts a map of brief faults and restarts. A meteor network publishes the first clean composite: the track, the altitude band, the brightness curve, the infrasound spectrum. It looks like a heartbeat laid over a map. Now the day does the thing all days do. It becomes evening. At sunset, the upper air ring that only satellites could see at noon becomes visible to everyone as a faint, high smear that glows and then dissolves as the last light slides out of the sky. Kids point, parents guess. A science teacher somewhere takes a picture and writes tomorrow's first 5 minutes. The world did not end. It hiccuped, and we heard it. What stays after the sound is not fear. It's a rule of thumb you will remember forever because you once used it. Bright flash, look away. Don't go to the window. Wait for the boom. If a city forgets, glass teaches again. If a city remembers, the same blast becomes a story instead of an injury list. And the deeper lesson lands quietly. The atmosphere is not empty. It is a shield 10 meters of water thick, poured invisibly over every street and field. It is a Whipple shield the size of a planet. It turns bullets into mist and then into light and air that push and fade. Nothing you did made that true. Everything you do decides how gently the day moves from flash to cleanup. When historians of instruments write their chapter, they'll say the networks were ready because we built them for other reasons. We learn to read lightning and storms and auroras. We learn to hear the planet's low notes.